Now that we've discussed the first law of thermodynamics, I think it's worth circling back and thinking a little more carefully about what is temperature. We haven't really defined it very carefully. We used the zeroth law of thermodynamics to say that all things that are in thermal equilibrium are at the same temperature, so we are implying that there is something sort of universal about temperature, but we really haven't defined it very carefully. So to set up this analysis, I think it's best if we introduce the ideal gas law. You've probably run into it at some point in your academic career, but if not, in an ideal gas, we assume that there is no interaction between the atoms in the gas, and that the gas can be treated as if the volume of atoms is negligible, as compared to the volume of the total gas. So these assumptions aren't strictly true, but they are a pretty good approximation under typical temperatures, pressures, and volumes. So the ideal gas law is that the pressure of a system times the volume of a system is equal to the number of atoms times the Boltzmann constant, which is 1.38, times 10 to the minus 23 joules per Kelvin, and that times the temperature in Kelvin. This is more commonly written using moles, with PV is equal to nRT, where N is the number of moles of atoms in the gas, and R is the gas constant of 8.314 joules per mole Kelvin. The number of moles is the number of atoms divided by 6.02 times 10 to the 23rd, and so then that's a value in moles. This is convenient since the number of atoms in a system is ridiculously large, and if we know the molar mass, then we can convert the mass to moles and back again very quickly. The temperature here is in Kelvin, pressure is in pascals, and volume is in meters cubed. One reason to bring this up is that an early thermometer that was popular is a constant volume thermometer. That means a sample of gas is kept in a quartz cell with something used to measure the pressure. Because the volume is constant and the amount of gas in the cell is constant, then the pressure in the cell is proportional to the temperature. This then works much like a mercury thermometer. I bring this up because the pressure of gas is proportional to the temperature. If the volume and the amount of gas is fixed, then we can use this to help understand what temperature really is. Okay, let's do a quick practice problem using the ideal gas law before moving forward. So we have a weather balloon filled with helium, and it has a volume of 6 meters cubed at 1 atmosphere and 30 degrees Celsius. So it rises above Roswell, New Mexico to an altitude at which the volume has expanded to 10 cubic meters, and the temperature is now negative 30 degrees Celsius. So our question is, what is the pressure of the balloon? So to start with, we use the ideal gas law. PV is equal to nRT, and because the amount of gas, the N, the number of moles inside the balloon, is fixed, that means that we can then make this into P1V1 over T1 is equal to P2V2 over T2. So doing this, we can then enter our numbers. So this becomes pressure is 100 kilopascals times 6 cubic meters divided by 303 kelvins. Notice we have to convert to kelvins for this. So 273 plus 30 gives us the temperature in kelvins of 303 Kelvin. Then that is equal to the pressure times 6 meters cubed. It's 10 meters cubed, and then divide by 243 Kelvin. Now we can then solve for pressure, and then multiplying by the left side by 243 and dividing by 10 cubic meters, that gives us a final pressure of 48 kilopascals. So it's basically these sorts of problems. We sort of give you 5 variables, and then you figure out the 6th one. So the real purpose of bringing up the ideal gas law here is to better define what is temperature. So to define it more clearly, let's go all the way back to Physics 201, and let's try to analyze the motion of a gas molecule in a chamber. So to begin with, we want to know what is the force that an atom in a gas exerts on the side of the chamber. To do this, I guess we should take a noble gas atom. So the only type of energy in this system is kinetic energy, and we'll put this gas atom with a mass m in a box with a velocity v. We would like to know how much force the atom exerts on the side of the box. So we will just look at one direction, the x direction, and try to figure out the force on the wall that is perpendicular to the x direction. When our atom collides with the wall, we want to know the force. Well, the force is the change in momentum divided by time, so what is the change in momentum? The atom will elastically collide with the wall, so its initial momentum here is going to be negative mvx, so it's moving to the left, and we're looking at the x component of the velocity moving to the left. And after the collision, the final momentum is going to be mvx to the right. That means that the change in the momentum of the atom is 2 times its mass times its x component of its velocity. That gives us the change in momentum, but what about change in time? If the atom is traveling with an x component of velocity vx, then we can figure out how often the atom will collide with the edge of the box. Well, velocity times time gives you distance, so if L is the length of the box, then the time between the collisions will be 2 times the length of the box divided by the x component of the velocity. The atom has to travel the full length of the box and back again before it collides with the same wall. It also should make sense that the time between collisions is inversely proportional to the velocity. The faster the atom is moving, the more often it hits the wall of the chamber. So cool. We've got the force against one wall of the chamber, and that is equal to 2 times mass times Vx divided by 2 times the length divided by the velocity x. So rearranging this, we get the force of one atom against the wall of the box to be equal to mvx squared divided by the length. The force is interesting, but when we're looking at fluids, we are usually interested in the pressure. So the pressure is the force divided by area. So we divide both sides of this equation by area, and we get pressure is equal to mv squared divided by length and divided by area. So remember, the length times the area is the volume, so pressure is equal to mvx squared, so something that looks proportional to the kinetic energy, divided by the volume. So I want to hold up for a second here and point out that we can set this to be pressure times volume is equal to something proportional to the kinetic energy. So you should be thinking you've seen something like this on the previous slides, and you are right. This is very similar to the ideal gas law, and we derived it using methods that any student who did pretty well in 201 should be able to work out. It's kind of beautiful. Okay, so it gets a little more complex here. So first up, we derived the above formula for a single atom. So for a system, we will need to multiply by the number of atoms in the system. So we're going to multiply by the number of atoms, and we will use the number of moles multiplied by Avogadro's number here to get the number of atoms. Next, we used the x component of the velocity squared, but the gas is moving in all directions. That means that the velocity of the gas squared is equal to the total velocity is equal to 1/3 of the Vx squared plus 1/3 of Vy squared plus 1/3 of Vz squared. So that means that Vx squared is equal to 1/3 of the total velocity squared. So our final derivation here is that pressure times volume is equal to 1/3 times the number of moles of gas times the molar mass times the average velocity squared, or the root mean velocity squared. Alright, so I'm going to maybe cheat a little bit here and work backwards using the ideal gas law. And from that we find that the root mean square of the velocity is equal to the square root of 3 times the gas constant times temperature divided by the molar mass. This tells us that if we know the temperature and the molar mass of a gas, we know the average velocity of the atoms or molecules in that gas. The velocity given is the root mean square of the velocity, which is if you take the velocity, you square it, take the mean of that value, and then take the square root. It's a little complex here, but all we really need to know is that this gives a pretty good representation of the typical velocity of an atom or molecule in a gas. Alright, let's do a quick example. So we have a sample of hydrogen gas at 10 degrees Celsius, and we would like to know the root mean square velocity. Well, the molar mass of hydrogen gas is 0.002 kilograms per mole. So we look at our formula, and we get the the root mean squared velocity is the square root of 3RT over mass. So we need the mass constant, which is 8.314 joules per mole Kelvin, times the temperature, which is 283 Kelvin. We need to convert to Kelvin here, remember, and then divide by the molar mass, which is 0.002, since hydrogen is diatomic. When we do the math on this, we find that the root mean squared here is 1,838 meters per second, which is really fast. In fact, the escape velocity of Earth is about 11,200 meters per second. I haven't mentioned it, but the velocities cover a pretty wide range, such that a small percentage of the hydrogen molecules here will have a velocity much larger than this root mean square velocity. It's not all fixed, there's sort of a wide distribution. For this reason, a small portion of the hydrogen gas will have a velocity greater than the escape velocity of Earth, and so hydrogen gas tends to be lost gradually over time. For Earth, this is not such a big deal, but for the Moon, you have a much lower escape velocity because the Moon is less massive, so a lot of lighter gases on the Moon cannot last because their velocity is too great and they just escape the Moon's gravity well, making it difficult to live on the Moon. Okay, so we've seen that temperature is proportional to the kinetic energy, but I'm still a little unsatisfied with the details, and we haven't really found a crystal clear explanation of temperature. So the kinetic energy of our gas is equal to 1/2 mv squared, right? Something again straight from 201. And we just found that the velocity squared is equal to 3RT over the molar mass. So let's plug that in. The kinetic energy is equal to 1/2 times 3 times the mass of the individual molecule times R times T over the molar mass. The molar mass divided by the mass is Avogadro's number, so that simplifies, and the ideal gas law constant divided by Avogadro's number is Boltzmann's constant, which we've mentioned before here, but we should highlight again. So this means that the translational kinetic energy of an atom in a gas is equal to 3/2 times Boltzmann's constant times the temperature in Kelvin. So if we know the temperature, we can use 3/2 kT to find the kinetic energy. This is completely universal, whether we're talking about hydrogen, carbon dioxide, or even pollen grains. When we are measuring the temperature of something, essentially what we are measuring is the average translational kinetic energy of its molecules. So things that are the same temperature have the same translational kinetic energy in its molecules. Or if we want to know the kinetic energy in one direction, say x, y, or z, then the kinetic energy in one dimension, or in one direction, is 1/2 kT. And that is the microscopic connection between temperature and motion. The average energy carried by each microscopic degree of freedom is equal to 1/2 kT. This is a very useful concept because if you want to know if a microscopic process is likely, you can calculate the thermal energy in every degree of freedom by using 1/2 times the Boltzmann constant times the temperature, and if the thermal energy is greater than the energy of that process, then it's going to happen very easily. So if the energy of something is, say, 50 kT, then it will spontaneously happen at 100 Kelvin. Okay, so you have some questions to do here. Some ideal gas law questions, some Boltzmann questions. So I think next up we'll think a little more about these degrees of freedom, but good luck with your questions.